Our goal is to be able to interpret the meaning of the value of a and b in the exponential function, ab to the x, and write exponential functions in the form f of x equal to ab. So we want ab to the x. We want to be able to write these equations, not just graph them or look at the graphs. But it's actually pretty easy because, again, the vocabulary makes a lot of sense to us compared to what we know from before. So we have two options for our equations. We can either have a growth or a decay equation. What kind of number was in the parentheses for the growth equation? 2. Is that number bigger or less than 1? Bigger. So our b value is going to be bigger. That means that the graph is going to grow. It's going to be going up. That makes a lot of sense. And if the number in the parentheses is less than 1, it's always going to be a positive number, so between 0 and 1. So if it's less than 1, what's that graph going to be doing? Decaying or decreasing. Very good. That's what we want to be able to do today and make sure we know that. So let's write that in some words. On this side, we know that A is still my what? What did we call it last time?
Y-intercept.
The y-intercept. So we know that that didn't change. But this b value right here, we're going to get more details about the b today. If the b is greater than 1 or more than 1, the function represents exponential growth. It should increase. If b is less than 1, it's always going to be greater than 1. So if it's between 0 and 1, but we'll just say less than 1 to make it easy for ourselves. What's the word again? What is that going to show me?
Decay.
Decay. Very good. So we have growth equations and we have decay equations. Okay. So let's look a little bit more detailed at that rate of growth, the b value. As an independent variable in an exponential function changes by a constant amount, so as x goes up by 1, like in this table, the dependent variable is being multiplied by a constant factor, which means it's a constant ratio. When else did we talk about the phrase constant ratio? Do y'all remember? How about common ratio? Okay, let me do this then. If you look at these numbers in the y part of this equation, how did I get from 2 to 4? Times 2. How did I get from 4 to 8? And how did I get from 8 to 16? When did we do that again? Haven't we done this already?
Yeah.
What kind of sequences were those? Were they arithmetic or geometric? Geometric. So really, exponential functions are just functions that are geometric sequences. So all of this is the same, just in a different notation. So if we look at this graph right here, we have a y-intercept of 2, and then the next number is 4. And if I did it again, the next time it would have a coordinate point that I could plot, it would be up here at 8. This would keep going, and it would be at 8. But of course, it kind of goes off screen there. So that number is going to grow and increase by the same amount every time. So again, we're just looking at this equation, making sure we understand it. We know that A is the initial amount, or the y-intercept. So that's what I'm starting with. In word problems, you'll look for words like starting value, initial value, first. And then the b value here is going to tell me how fast it's growing. I want you guys to do something for me, though. I want you to add parentheses here. So I want you to put that b number in parentheses. We're going to be putting them in parentheses all day, so I want to make sure that that's on your notes for today. Remember, again, if that b value is bigger than 1, you're going to see exponential growth. And if that b value is between 0 and 1, or less than 1, it's going to be decay or decreasing. Now I'm going to be asking you to write, don't flip it over yet, I'm going to be asking you to write equations similarly to when we wrote equations for linear functions. Does anyone remember when we had a linear function and we were given a table of x and y values, how we could get the equation? Does anyone remember what we did when we wanted to get the equation? Put a table in on Desmos and then do what? Put all the numbers in there and then do what? Fancy number 9, right? Okay, so here's the thing. Fancy number 9 is fancy slope-intercept form. There's a fancy exponential function. if we did all those same steps in Desmos and then use the fancy version of this equation, which is y1 squiggly line, a b to the x1, I need y'all to write that down. This is going to be how we're going to write equations today. We're going to use technology to be able to do this. So this fancy version of the exponential function, it's not on your formula chart, so you do have to know it, but it's just alphabetical order, a, b to the x. You give x and y a 1, just like you did with linear, and you make the equal sign a squiggly line. Yes? Okay, do you have that written down? Does it look exactly like mine? y1 squiggly line, a parentheses b to the x1 power. Okay, cool. Now we can flip this page over. This is what questions might look like for you when I'm asking you to write an exponential function. It says the table contains some points on the graph of an exponential function. We got a table. Anytime you see a table or coordinates or a graph, your brain should start thinking, I could probably make this fancy. Write a relationship or a function that represents the same relationship. So again, guys, we're just going to be doing y1 squiggly line. What were the letters again?
A, parentheses, B, X1.
To the x1, yeah. To make it an exponent, you say the words to the x1. Okay, so let's do it. Everybody open up Desmos test mode, please, and I want you to type that table in just like you see it, like we've always done for tables and linear functions. We're just not going to use fancy number 9. We're using the fancy exponential function. I'll give you some time to do that. Now that I've found those numbers in Desmos, now that when I go to write this equation, it's going to be y equals, what was the a value on your Desmos? 0.25. And what's the b value in your Desmos? 2. Now I forgot something on what I've written right here. What did I not put up there? The little x. It's an exponent of x. Very good. That needs to be there. Now this makes sense to us because we learned last time that the y-intercept is partnered with 0. So look at that table. So you have something partnered with 0, right? Isn't that my y-intercept? Yeah. That's my first number in this equation, 0.25. That's my y-intercept. That makes sense to me. Also, what makes sense? What's up?
Does that mean you don't have to do it?
If you know what the pattern is and you know what the y-intercept is, no, you don't have to. They won't always give it to you. So it is still good to know how to do it because sometimes the tables won't show you the y-intercept. One thing else, that's not a real English sentence. One other thing I'd like you to notice is, let's just go to the easy numbers. How did I get from 1 to 2? How did I get from 0.5 to 1? How did I get from 2.25 to 0.5? Why do you think that number 2 is now in the parentheses? That's the pattern. That's the number I'm multiplying by. So this totally makes sense. We can totally do this without the technology, but we have the technology to be able to write these equations anytime. What's your question?
How come the squiggly line equation has a 1 by the exponent, but the other one doesn't?
It's a good question. That's part of the programming of Desmos. Any of the fancy versions of your equations are going to have a subscript of 1 next to x and y. And that's because if you look at your table on Desmos, what's at the top of your table? Does it just say x and y?
No.
Or doesn't it say x1, y1? Okay, so you're telling Desmos use those numbers, the x1, y1. That's it. That's the only reason. It's just part of programming and how the programming works. Okay, I want you guys to try number 2. You can use either method to try to solve this. And I want you to make sure you know how to use both. So Desmos, or just by looking at it, I want you to try to write the equation that represents the same relationship as this table. Once we have that table in our Desmos and we've used fancy version of the exponential function, which is y1 squiggly line a times b to the x1 power, you just get the numbers for a and b out of the technology, and you have y equal to, what was the a value? 15. And then what's the b value? 0.83 to the x. Now, there's something cool I want to show you in Desmos, because this particular question actually came from the STAR test, and the STAR test didn't have an answer choice that looked like this. It had it in fraction mode. So here's the thing. If you just type 0.83 into Desmos and change it to a fraction, it won't match one of the answer choices. Here's why. So like I said, this could also be the answer choice y equal to 15 times 5 over 6 to the x power, because it's the same thing. Okay, let's look at the third example on this page. Instead of a table, what pieces of information were you given? What stimulus were you given?
The Y-intercept.
We were given the y-intercept because we can see it on a graph. What's the y-intercept here? Okay, great. I already know that that number is going to be in my answer because it's going to ask me for what is the function represented by the graph. The problem is finding the rate is kind of hard. First thing we know, should the rate be bigger than 1 or less than 1?
Less.
Why less than 1?
Because it's decay.
Because the graph is decaying. Okay, good. I'm glad we know that. Here's what I need us to do, though. To be able to use technology for this one, we need 3 coordinate points. Well, we already found 1 coordinate point. Isn't this point right here 0, 15?
You 1,5.
Oh, you see this one, right? This is 1, 5. Can we find another good one?
Negative 1,45.
Negative 1, 45. I like that one too. So negative 1, 45. When we have 3 coordinate points, we have x's and y's and x's and y's. What can we do with these x's and y's in an organized manner on our Desmos? We can put them in a table. Oh, snap. So that's what we're going to be doing. I need everybody to take these numbers and put them in their Desmos again because we can still use y1 squiggly line times y1 squiggly line a times b to the x1 power. Yeah, those are...
Or is it going from the negatives to positives or positives to negatives?
Doesn't matter as long as they're together. I always put them in number order, so negatives to positives. So let's do this one. So since we've got those numbers out of Desmos, we can go ahead and use them. This is going to be y equal to 15 times 1/3 to the x power. Or if you wrote it as 15 times 0.33 to the x power, that's fine. You're going to see the answer choices on most of the STAR questions as actual fractions instead of the decimals. They kind of go back and forth, so we just need to be ready for either of them. Yes, sir. Yes. Okay, we're going to check and make sure we understand this one. You have this graph right here. Before I send you off, together we will find the coordinate points, but I'm going to let you finish the problem on your own. Can anybody find me a good coordinate point here? 0, 4,000. Okay. Can anybody find another one? 1, 8,000. Does everyone see how we're getting these numbers? No, we don't see. Well, if that's a no, we're going over to 1 and we're going to go up until it meets the line. And if that's at a perfect hash mark, a perfect coordinate, we're going to write it down. 1, 800. I need one more coordinate point. What can we use? 2, 16,000. Okay, I'm going to let you finish on this one. I want you to write the equation for me. What do we get for this one? What's the y-intercept? 4,000. So that should be the first number in my equation given out of Desmos. Is that what Desmos gave you? Yes. And then what's happening to these numbers every time? Multiplying by 2, they're doubling. 4,000, 8,000, 16,000. That's all doubling numbers. So my b value is going to be 2 because it's doubling, while the y-intercept is 4,000. Now that makes sense to us a lot because we know some things about these graphs. So I don't want us to lose that information. Details about the exponential growth and decay functions. So normally you've been seeing these functions with one number in the parentheses, but we sometimes have 2 numbers in the parentheses, and it's when we're given more details about what's happening. So what we need to know, again, when we had just the regular number b, we knew that it was growing if that b value was greater than 1, and it was decaying if the b value was between 0, 1, or less than 1. But when we look at the details of what's called the rate of growth, that b value is either going to be 1 plus this rate that we're going to learn about, or 1 minus the rate. Why do we think we would be adding and subtracting? Why is there a difference there?
Because growth is going up, which is adding, and then decaying is going down, so it's subtracting.
Absolutely. Did y'all hear him? Growth is going up, so we have to be adding a rate. Decay is going down, so we're going to be subtracting the rate. Now this rate, this R value, is going to be given to us as a percentage. We did a GIM-kit at the beginning of class to remember how to change decimals to percent. So that's going to be important for us in this little section. So right now, we have a more expanded version of our exponential function. A is still my y-intercept, and B, the parentheses, is still the growth or decay factor. But we're going to get more details now about whether it's going to be a growth or a decay and by what rate we're growing and decaying. So this R value is called the rate. It's R. It helps us create the B value. Okay, this is going to be mostly word problems that we're going to see here. So we're looking for these vocabulary words in a word blurb. I want you right now, though, to put a big star, circle, underline, highlight this important note right here. It's super important. I said it out loud, but now you can read it. The rate must be converted to a decimal. And if you don't remember how to do decimals to percents, even though we did it on our warm-up, it's called the Dr. Pepper rule. And if you've never seen this before, here you go. If you have a decimal and you want a percentage, which direction should I move the decimal?
Right.
Dr. Pepper, towards the percent. If I have a percent and I want a decimal, which direction should I move the decimal?
Left.
And twice, because Dr. Pepper has 2 letters. So if you need help remembering that, it's the Dr. Pepper rule. Decimal to percent, percent to decimals. Same letters as Dr. Pepper. Okay, let's look at example number 5 here. It says, in the year 2006, an annual music festival held its first gathering. Each year, the attendance at the festival has increased by 3%. Write a function that models this situation if the attendance at the first festival was 550,000 people. Here's a couple things I need us to look for. What does this word increased tell me? We're adding, and that is growth. Amazing. What's the rate that this is growing?
30%.
Did that give me B or R? R, which means that I need this as a decimal. So what is 3% as a decimal? 0.03. We move that decimal place twice, Dr. Pepper rule. So 0.03 is what I'm going to be using in my equation. The only other thing I need is a Y-intercept, or an initial value. Well, how many people initially went to this festival? 50,000. That was the first festival. So that's the initial festival. What I'm filling in this equation is the 50,000 for the first number. And then I use the expanded version. I'm going to do 1, and then do I do plus or minus?
Plus.
Why plus again? Because it's increasing. And then I'm going to put that rate. I'm going to close parentheses, and I'm going to put my exponent of x. Right? We've just filled in what we know. We knew it was increasing, so that's plus. We knew the rate was 3%, so 0.03. And we knew its initial festival was 50,000. All we have to do to finish this up is clean up or simplify this parentheses. Super easy. Yeah, no big deal. Watch this. We're just going to go to f of x equal to, that 50,000 does not change. And then I'm actually just going to add these numbers together. What is 1 plus 0.03? 1.03. And boom, I'm back at having a rate just like the ones we did on the first page. We just put it together with more details about what percentage we're growing at. This is more like what you would see in like a real life scenario. Banking, if you ever you should get a bank account, you get interest rates. This is how all of this is determined. So this is math you actually need. This is money math. That would be, depends on the interest. Interest on debt, yes. Interest on money you put in the bank's paying you. Because you're giving the bank your money to hold, and the bank has to pay you for that.
Well, isn't there, okay.
We'll talk about how banks work later. We get to some money stuff after the STAR test. Don't worry, I'll teach you how banks work.
Really?
Yeah. We're going to go on. I want you guys to try example 6. I'll read it out loud and help you find the stuff, but I want you to put it all together. It says, an engineering major at Texas A&M, whoop, graduates and gets a job working for Texas Instruments. Her starting salary is $65,000, and she has been promised a 7.5% raise each year. Write a function that models this situation. What are some things that we know? It's a good starting salary. It's more than teachers make, so
No, the 7.5.
it's pretty good, actually. At each year, consistently, it's pretty good. Okay, what's the Y-intercept? What's the initial value here? 65,000. Now, is this going to be growth or decay?
Growth.
Why? Because we're getting a raise. Raise means your money is going up, so that's a growth. And then what's my percentage that it's growing?
7.5.
That's a percent. So what is it as a decimal?
7.5.
0.75.
You got to move it twice. So 1, 2.
I put 0.75.
That's only moving the decimal one time. Remember, you have to move that decimal twice. Dr. Pepper, 2 letters. Okay, I'm going to leave you here. I want you to finish writing it. Plug in all of these numbers and then simplify for me, please. Okay, so I'm seeing some really good stuff. Here's what I would have done. I start filling this out. F of x equal to the Y-intercept, $65,000. That's what the starting salary is. Pretty good starting salary. The 1 is always there, and then this is going to be plus because it says it's a raise. And then the decimal version of that percentages, always to the x power. Then I can just simplify this down. F of x equal to, still 65,000. But instead of having 1 plus 0.75, I'm going to have 1.075 in my parentheses. That's my factor that I'm multiplying by each year to see how much this engineer would make at TI, which is pretty cool. Okay, I want you to try one more, and this time I'm not going to read it with you. I want you to read it from start to finish. Number 7 is yours. All right, I'm seeing some really good stuff. Thank you for trying. Okay, what are some key words out of this that you highlighted, circle starred, underlined?
Decrease.
Decrease. Does that mean we're going to use plus or minus?
Minus.
Awesome. What else did you do?
I don't know, 36.
The 36,000 was your Y-intercept.
36,000 was my Y-intercept, so I know that's going to be my first number. What else?
0.05 was the rate, or 5%.
Yeah, we have 5% right here as the rate. If I change that to a decimal, it's 0.05.
Will it always be 2 numbers?
What do you mean?
Only the percent and like the Y, I guess.
Essentially, yes, because those are the only 2 things you need to substitute in, and then you just need to know if it's increasing or decreasing. The 1 is always there, so you don't ever have to look for something for 1. So if we start plugging this in, this is going to be f of w. Fun fact, it told you to use w. If you used x, that's fine, don't erase it. But it technically said to use w as your equation here. Then we have 36,000. And then 1 minus 0.05 to the x power. One thing I wanted to point out to you, I'm okay with you using the commas in numbers to separate 36 and its thousand. But if you type that into a calculator, either the yellow calculators or online, don't put a comma. It doesn't need it. That's for humans to help us quickly tell how big the number is. Calculators don't need it. So that, no, humans programmed the calculator, so we control the calculators, but it's only as smart as the person using it. So we're equally smart. We need to destroy them before they make their own decisions. Nice. I like that little doomsday moment. All right, so this is 36,000. And then if I actually do this math, 1 minus 0.05 should be 0.95 or 0.95. Whoa, what? What happened?
Come here, please.
What happened?
Come over here. Where did I...
Well, we're subtracting. Oh, this is a really good point. Are we adding these numbers? No, it says to subtract them, so we actually have to subtract the numbers now so that it decays. Oh, wild. Gotcha. Okay, this next problem is kind of interesting, so we're going to do this one together. It says there are 64 teams who qualify for the NCAA basketball tournament. True facts. In each round, half of the teams are eliminated. That's how tournaments work. Write a function that can be used to find the number of teams remaining in the tournament at the end of a certain number of rounds. Okay, let's look for words that we know. How many teams are there initially?
64.
So what is the 64? Is it my first number?
Yes.
Yeah, it's the Y-intercept. Okay, then I don't see another number at all.
Half.
It says half. What is half, though?
0.5.
So half is 0.5.
Can you write it in percent?
So half is 50%, right? A whole is 100%, so half is 50%, which means you guys are right, 0.5, which is a half. That's going to be my rate. Now, is this rate going to be added or subtracted? Y subtracted.
They got eliminated.
Eliminate. Plus, we know how tournaments work. It shouldn't be growing. The number of teams in the tournament should be getting smaller every time. So it should be decaying or subtracted. Okay, great. So here's my function. We have f of x equal to what number? 64. Open parentheses, 1 minus half, which is 0.5 to the x, or 0.50 if that helps you see that it was 50%. Now it's 0.5. I moved the decimal twice. I see some confused faces. Did I just confuse you?
Nah.
Do we know that 0.5 and 0.50 and 0.500 are all the same number?
Yeah.
I think it's because people know that half is 0.5 instead of them going from 50% to a decimal.
So remember, a half, like Ms. Jackson is saying, is 50%, is 1/2, or is 0.5. All of those are the same, depending on the representation you want.
So you don't do the step where like you move to this one, like 2 cents to the left?
If you get a percentage, you need a decimal. So if you see half and your brain already thinks in decimal form and thinks 0.5, you don't have to change anything because you're thinking in decimals. But if you're given a percent or you think in percentages, you're going to have to move the decimal. That's a good question. Okay, and then we have f of x equal to 64, open parentheses, and then what number's in there? 0.50. 1 minus 0.5 is 0.5. So it's kind of funky that it ends up being the same number. That's just because 1 minus 0.5 is 0.5. Yes. It does not. That was a good question. It does not need the extra 0. 0.5 gets the point across. But it could have the extra 0.
Ooh, that's a lot of questions.
Okay. Okay. So sometimes we're going to have to work backwards to figure out the rate. Okay, this time I'm not given a word problem, I'm given the actual equation. So let's zoom in on these equations for a second. We can answer this first box. For that equation, y equals 50 times 1.025 to the x. Is that going to increase or decrease?
Increase.
How do you know it's increasing?
Because that 1.
This number in the parentheses is bigger than 1, so it's going to increase. Which means, should the graph be going up or down?
Yeah, up.
Up. Okay, so we know it should look something like that. That's great. How about the second one?
Decrease.
Why decrease?
Below 1.
Because the number in the parentheses, the b value is less than 1, so it's going to decrease, which means it graph should decrease. What about the last one?
Decrease.
Decrease as well, because this number is less than 1, so its graph should be going down. But we need to figure out the rate at which these are going up or going down. Not the factor, not just the number in the parentheses, not b. We want to figure out r. So we're going to have to use the idea of absolute value here. Does anyone know what absolute value is?
I forgot.
Distance from 0.
Yes.
So how far away is 3 on a number line from 0?
3.
How far away is negative 3 from 0? 3. So it's just like basically chop off the negative sign. Is absolute value. It's just the number without the negativity. Okay, now that idea is going to help us here because we want to figure out what the R value is, what the rate is for each of these. So what I'm going to need to do is take the number that you see, this 1.025, and subtract 1 from it. 1.025 minus 1 is 0.025. Now that's the decimal version. What's the rate?
102.5%.
Oh, okay, so remember, if it's already a decimal and I want a percent, which direction am I moving the decimal?
You're talking about the 2.5%. That's like 2.5%.
It's 2.5%, and it's a 2.5% growth.
I thought you were talking about the other number.
Oh, no. So what we've done is we've been able to look at the condensed version, 1.025, and change it into its rate of 0.25. Let's do the next one. So again, I'm going to take the number in the parentheses, 0.975, and what am I going to subtract from it? -1. Now you might need a calculator for this one, but go ahead and type this into your calculator. 0.975 minus 1. definitely negative. Negative what?
So,
Is it 0.025?
oh, negative point, yeah.
If it's negative 0.025, I just need the absolute value of that for the percentage. What's the percentage rate here?
2.5?
2.5 again, but this is 2.5%. Is it growing?
No.
Decaying, because that was a negative number. And we knew that because the graph should decrease. We already kind of talked about that.
No.
Now let's look at the last one here. Tell me again the process by which I would find the rate. What number do I put down first? Bless you.
0.1.
And I'm going to subtract what? And what am I going to get? I want to see what the rate is. And so I have to get rid of the 1 from the parentheses to be left with just r. Negative
Negative
0.75.
So you do that in decimal?
So yeah, you would need to actually do this math. 0.25 minus 1 would give you negative 0.75.
It's like
Oh,
1
you're
to 100.
decreasing?
You're subtracting
Like that, isn't that weird? How do you know you're decreasing?
Oh, that's a good question. Hey, Angel just asked a good question. How did we know it was increasing or decreasing again?
Oh,
The number in the parentheses.
Oh, it's smaller.
Oh.
Smaller than 1, decrease. Bigger than 1, increase. Okay, so we have negative 0.75, which means the rate is what? 75%. Is it growth or decay? Because it was a negative number, plus we know it's decreasing. Yes, sir?
Would it be increase or decrease if you got the number 1, like just 1?
It would not be an exponential function if it was just 1. It would be a constant function, which you'll talk about in Algebra 2. So it will never just be 1. It will have to be something bigger or smaller than 1.
Is it because then it's just going to be a straight line?
Yeah.
See?
Because imagine multiplying by 1 every time. What's 2 times 1? Times 1. Times 1. Times 1. You say it will never change. It's called a constant function. So it has to be more or less. That's actually a really cool concept to talk about. Okay.
Oh, I gotta write it down.
We're going to look at these questions. These are really good questions, and these are what they look like on standard tests. So you're
4 mini questions?
this is 4 mini questions, yeah. Okay, if we look at number 9, and number 9 only, it says a student used f of x equal to 3.00 times 1.042 to the x to show the balance in a savings account will increase over time. What does the 3% represent? Sorry, not 3%, 3.00. What does this number? The y-intercept. Very cool. I like that we know that. But in real life, if this is her y-intercept, this means that that's the initial amount that this person put in the savings account. So what I want you to start recognizing is that the y-intercept, every time you're given a y-intercept, is also called the initial amount. That works for any kind of function that you have. When we did linear, our y-intercept was the initial amount. We're here in exponential. The y-intercept is the initial amount, the starting amount. It's going to be the same for quadratic when we get there. Now let's do the second part here. It says interpret the meaning of 1.042. What are some things we know?
That's
I want our brain to start thinking immediately. Should this graph be going up or going down?
it's going up.
Why is it going up?
Because it's
So this shows that we're going to have a growth. Should be going up. And then I want us to figure out what the rate of growth is. We should be able to interpret that. How did we just, up at the top, how did we just find the rate? Wait, just in the top part, what did we do? So if we take this number, what do I do to find the rate? Add 1? Subtract 1. 1.042 minus 1. Which means, what's the rate? Okay, I see some confused faces. Where are we confused?
Why you subtracting when you put as growth?
It's a good question. So remember, the regular formula is 1 plus some number r. If I use algebra to find r, I would need to subtract 1 to find r because I'd have to minus 1 on both sides. I'm doing the algebra for you.
It's a lot to like hold in.
Oh, it 100% is. I understand that. But we're just working backwards. It's like a little puzzle. We know what the b value is. We want to figure out what the r value is. Now, if I got this 0.042, what's the rate? 4.2% growth. Why was it growth again?
Because the virus was over 1.
The b value is greater than 1. Okay, amazing. I want you guys to do the same thing for the problem right underneath it. Look at the problem right underneath it, and I want you to answer its 2 questions. It asks them in a different order, so make sure you actually read the question. But I want to see if we can interpret A and B. That's one of our goals of today, to figure out what these A and B parts of the equation tell us. All right, so this next one right underneath it, it says the function y equals 22 times 0.94t represents the population in thousands of people of a town after t years. Interpret the meaning of 0.94. What did you guys say?
It's decaying.
It's decaying, so my graph, should it be going up or going down? Down. Now, we need to figure out the rate that it's going down. What's the rate that it's going down?
0.49
Minus 1.
1.
And what'd you get when you do that?
Negative 0.6.
Negative
0.06.
Which is what rate?
That's not even a curse word. It's in the Bible.
Which is what rate? It's 6% decay. Okay, that's some things that we know just by looking at this. What do we know by looking at 22? It's the Y-intercept. Amazing. And what does that Y-intercept tell me about this town? Okay, cool. So I have a question for you. The initial population of this town, what was it?
22.
So there's only 22 people who live in this town?
No, 90.
22,000.
22,000 people. It told me that it's measuring in thousands. So math likes to do this a lot, where we're like, well, if everything's in thousands, we'll just chop off three zeros and make the number smaller, but we just know we're measuring in thousands. So make sure you read that part. There's not 22 people in this town. There's 22,000 people in this town.
Weird after I said it.
Right? Yeah. 22 people. That's not enough. It's a very small town.
That don't sound so bad. You know everybody in town.
That would be super annoying. Everybody be all up in your business.
Not really.
Yeah, really.
Okay.
Just know how to keep your